Arendelle-ftl. This is a greeting phrase in Quenya language used by nodal elves in the famous novel The Lord of the Rings and the Silmarillion. So much for this. Let's begin today's astrophysics seminar. Today we will talk about the radiative models and the HR diagram. For the star, the energy transport can have two main mechanisms. The first one is the radiation, which we will talk about this time. The second is convection, which we will talk later. So today we are mainly talk about the radiation models of stars. Why we should talk about the radiation models? Because at the end of today's seminar, we obtain a very significant conclusion that for stars, if the ages and the initial chemical composition is given, then any stellar parameters can be expressed by a single stellar parameter, just as, for example, the stellar mass or the stellar radius r. And in particular, the plot of any two such parameters shall be one-dimensional, particularly the plot of luminosity L versus the effective temperature T. This plot is called Hertzsprung's Russell diagram, or just HR diagram, which we'll see in the end of today's seminar. Now let's begin our calculus. First, let's introduce photon distribution function L, n x u t d square n hat d nu, which represents the energy per volume at position x time t of photons within the solid angle d square n around the unit vector n and within the frequency interval nu to nu s d nu. Notice that the solid angle d square n is just we can express it in the spherical coordinates, and this expression will be very useful. So we explain here. So a unit vector n can be expressed as 1 theta phi in the spherical coordinates. This theta phi. So we can use the definition of the solid angle to derive the differential of it, d omega. R. Obviously, it equals ds over r square. And according to what we have learned in calculus about spherical coordinates, ds is just r d theta times r sine theta d phi. So we obtain the differential of solid angle is just sine theta d theta d phi. Now let's verify important property that the solid angle of a sphere integrate from 0 to pi sine theta d theta 0 to pi d phi. Well, according to simply calculus we obtained for pi, it's just indeed the solid angle of a total sphere. Now let's continue. We have introduced the photon distribution function L. Now, if we want to calculate its change, we should analyze the contributions to it. In radiative models, there are 4 main contributions to the photon distribution L. The first is transport. Well, L. If nothing happens to the radiation, then obviously the photons at time t as tt, position x, and direction n will just the same as the photons at time t, position x, minus cn dt, and direction n. So according to this, we'll obtain L n x nu t as dt equals L n x minus cn dt nu t. And according to this, we can easily obtain partial t L n x nu t transport equals minus c n dot multiply the gradient of the distribution function L. This is the first contribution to the distribution L. The second is so-called absorption. Well, an absorption process means an incident photon disappears without producing another photon which direction is correlated to that of the incident one. It's different from the scattering process, which we shall discuss later. So let's introduce the net fraction of radiative energy of frequency nu absorbed at position x time t in the interval t as dt is c chi absorption x nu t rho x t dt. This is the absorption opacity, which characterizing the process of absorption. Now, according to the definition, we obtain partial t L n x nu t absorption equals minus c chi absorption x nu t. Write it again. Nu t times rho x t L n x nu t. Okay. The third contribution is so-called scattering. A scattering process means there's an incident photon disappears, and the final photons will be producing, while the final direction is different from the initial one, but these two directions are correlated. So let's introduce the fraction of the radiation energy frequency nu and direction n at position x and time t be scattered to a new direction n prime. It's chi s n to n prime. This is the original direction, and this is the direction where the photon be scattered to x u t. rho x t dt. So now there's something different. There's a little different from the absorption process, because if we want to obtain the partial derivative of time over time of the distribution L, we shall not only consider the scattered from direction n to n prime at time t, but we should also consider the scattered from n prime to n at a little earlier time. To deal with this problem, we should assume that this chi-s rho, this is the mean free path is so small that any photon scattered to position x at time t can only have been scattered at the position x prime and t prime with the same distribution L and mass density rho, which means L x t equals L x prime t prime rho x t equals rho x prime t prime. With this assumption, we obtain the partial derivative over time of L n nu t scattering equals 0 x t integrate over the direction n prime minus chi-s n to n prime x nu t L n x nu t as chi-s prime to n x nu t L n prime x nu t. Okay. So this chi-s is the coefficient characterizing the scattering. Now, the final contributes is the emission process. Let's suppose the radiative energy emitted at any direction n per time per frequency per solid angle at the time t and the position x is partial t L x nu t emission equals j x nu t rho x t over 4 pi. Well, this j is the coefficient characterizing the medium and the radiation field. So combine all four contributes, we finally obtain the equation partial t n x nu t equals minus c n dot multiply the gradient of L nu t minus c chi absorption x nu t rho x t L n x nu t as the scattering term C. No, it's not the scattering. C scattering term. d square n minus chi s n prime prime u t l u t as chi s n prime n x u t l n prime x u t. And finally, the emission term j x u t rho x t over 4 pi. Now let's suppose the air and other stellar material are unchanging over time t. Now, and we can obtain immediately the following significant equation. C n dot multiply the gradient of n. Notice that the variable not include time t here. Close. Oh, can I just no? There's any way to copy it. Copy, paste. Only need a little. No t here, no t here, no t here. New, yeah, and following will not change, just copy them. Copy, paste. With a little change. Eliminate the variable t. Oh, yeah, just like this. Okay, it's done. So we obtain this. This is a very significant equation, which we will use in following discussion. Now let's introduce three three fundamental quantity. First, the radiative energy per volume per frequency nu, epsilon radiative. Its definition is integrate over direction n l x nu. Second is the flux vector of the radiative energy per frequency nu. Psi is the component nu defined c integrate over direction n I l x nu. Yeah. The third is the special part of the energy momentum tensor of the radiative energy per frequency. Capital theta ij x nu integrate over n I and j l x nu. We can use the above equation to derive the relations between these three fundamental quantities. Notice here that I, J, K are just the coordinates of a Cartesian coordination x, y, z. It just means this. Okay. So let's begin. If we integrate the above equation over direction n, just integrate over the direction n, we will obtain the following equation: divergence of the flux vector equals minus c chi absorption x nu rho x, the radiation x nu at j x nu rho x. Okay, notice that the integrand of the this is the absorption, yeah, scattering term, yeah. The integrand of the scattering term is antisymmetric with direction n and direction n prime. So if we integrate the whole equation over the direction n, this term will vanish. Wait a minute. Okay, so we obtain this important equation. So for an homogeneous mediums, the homogeneous medium means these quantities are independent of the position x. We can obtain 0 equals minus c chi absorption rho radiate as j rho, where j equals, it can implement that j equals c chi absorption epsilon radiation. This is for homogeneous medium. We also can consider this condition is valid at a given position x in a real star. So for inhomogeneous real star, we can just write j x nu equals c chi absorption x nu epsilon radiation x nu at yeah, this I should use little epsilon. Okay, the foot this kind different. Notice that this little epsilon is the energy generation from the rate of energy generation from a nuclear reaction per gram per frequency. Actually, I should use this one. Okay, I use this one. It's more appropriate. Right. This is the rate of energy generation from nuclear reaction. Okay. And finally we can use this equation to substitute in the above one, obtain divergence of the vector flux, the flux vector x nu equals epsilon x nu rho x. Okay. Yeah. First equation. Second one. If we integrate this equation before, if we multiply the ni and integrate in to the equation and integrate it over direction n, just mean this, we will obtain the following equation. equals minus chi absorption x mu rho x and psi I x mu minus 0x I chi scattering to n prime x mu l n x mu minus chi scattering n prime to n x mu l n prime. I should write n hat, yeah, n hat must start at n prime x mu. And notice here that this time the emission term will vanish because the mathematics tricks. Now, because the this emission term is independent of the direction n. So if we multiply it with ni and integrate it over the direction n, it's just the same as direction this one. A constant times ni d square n. And we can prove that for I equals to x, y, z, it all vanishes. For example, I can use an x. I equals x. We can just calculate as an example. Then an x equals sine theta cosine phi. So this integration will become 0 to pi sine theta square this theta integrate from 0 to 2 pi cosine phi d phi. And it's obviously 0. For ny and nz, it's the same. You can verify it easily. So the emission term vanishes. Okay, just a simple tricks. Now, how to deal with this one? We define two new quantities. Define just definition. Chi out x mu define d square n prime chi scattering n prime x mu, and the I component of n prime times chi in equals integrate over direction n. The I component of direction n chi of scattering n prime to n x mu. With this definition, the above equation can be rewritten as this one. Can be rewritten as C I j x mu was minus chi x mu rho x psi I x mu. Okay, well, this chi is the total opacity equals the absorption K as chi out minus chi in. Okay. This another important equation. So if we want to find the explicit expression of chi-in, we can just contract it with the direction and just like this, and a direction and prime. Yes, direction and prime. Just use this operation and in the other side, and we can obtain chi x nu equals integrate over d square n prime, a scalar product of n and n prime times chi s chi. Yeah. Serious? Don't have enough power. Embarrassment. Really embarrassment. My pencil has not enough power. Let's suppose here. Suppose here. Okay, let's continue. I'm sorry about my Apple Pencil. Okay, so let's continue our seminar. Chi-in can be explicitly expressed as this chi-out. Oh, no. Contracted with the direction ni prime. Yes, just like this. And we can obtain chi scattering n prime to n x nu. Well, notice that here that we have an assumption about the coefficient chi-s, that if we assume this coefficient is invariant under the exchange between the final and initial direction, which means n prime to n is equals n to n prime. That's an assumption about the coefficient, this coefficient chi scattering. So obtain d square n prime, the scalar product of n prime and n times chi s n to n prime x nu. Yeah. Notice that the scalar product is independent of the order of the n prime and n, and the integrable variation, we can change it. Yeah, we can just change it, and the integral will be the same. Notice that. So let's verify one thing about the property of scattering. So if the final direction and the initial direction is the same, then the scattering process does not exist at all. So chi-out minus chi-in should vanish. Let's verify it. Chi-out x nu minus chi-in x nu. Use the explicit expression of chi-in we have derived just now. We obtain integral over direction n prime 1 minus the scalar product of n and n prime times chi s n prime to n to n prime x nu. So if n prime equals n, then this coefficient should vanish, so the whole integral vanishes. And this is indeed consistent with our physics interpretation of scattering process. So we further assume that the free path 1 over chi rho is so small that the distribution function L is independent of direction n. So Ln x nu will tend to Lx nu. In this new assumption, this assumption will we can use this assumption in the interiors of stars instead. But we can't use it in the surface of stars. That should be noticed. Okay. This assumption records definition of the spatial part, the energy moment tangent, and the flux vector. According here, L is if L is independent of n, then this integration will only about Ni and J. Okay, and we can derive a very simple relation between capital theta and psi. That is in the interior stars. We'll have capital theta ij x nu equals 1 over 3 delta ij radiation x nu. Yeah. Notice that another mathematical trick here. This integral ni nj dn square. When I not equals to j, it vanishes. You can just easily verify it by calculate nx, ny, nz. Just calculate each interval. We can here we just perform one examples, nx and y. Yeah. It equals 0 to pi sine third power of sine theta d theta, integral from 0 to 2 pi sine phi cosine phi d phi. This one obviously equals to 0. And when I equals to j, we can prove that it equals I 4 pi over 3 when I equals to j. Or perform an example as well for nz. We have integral from 0 to pi cosine theta square sine theta d theta equals 0 to 2 pi d phi. It equals 4 pi over 3. Yeah, you can easily verify each integral. So with these mathematical tricks, we obtain this formula. And in the interiors of the star, we can assume the radiation have a thermal equilibrium with local matter at temperature T. So we obtain that epsilon radiation x nu equals b u tx. Well, this b is just the Planck blackbody distribution with which we have been familiar when learning statistical mechanics. B U T. equals 8 pi h over third power of c times nu third power of nu over e h nu over kt minus 1. This k is the Boltzmann. This k is just the Boltzmann constant. Okay. So, right, that's right. Well, recall the equation we have obtained before and substitute this equation and this equation into it, we can obtain another significant equation, C times the gradient of B, u tx equals minus 3 chi x nu rho x psi x nu. Okay. So we have derived the relation between the fundamental quantities we have just defined. Now let's consider the specific case of spherically symmetric star of great interest. Spherically symmetric star. Let's consider the structure of the spherically symmetric star. Now the flux vector can be written as 2 L R nu 4 pi r square ER. For spherically symmetric star, we should calculate in spherical coordinates, of course. And this LR nu is just the total radiant flux per time per frequency nu through a sphere of radius r. Okay. Before we continue to calculate, we should recall some basic formula about gradient and divergence in spherical coordinates. Yeah. We should record this first. For scalar f, r theta phi, its gradient in spherical coordinates can be written as partial f partial r er as 1 over r partial f partial theta e theta as 1 over r sine theta partial f partial phi e phi. And for vector f equals f r e r as f theta e theta as f phi e phi. The divergence of it in spherical coordinate can be written as 1 over r square partial r square times fr as 1 over r sine theta partial theta sine theta times f theta as 1 over r sine theta partial f phi partial phi. Okay. Use this gradient and divergence formula in spherical coordinates. We can transfer the significant equation we have obtained before. Epsilon x nu rho x and C times the gradient of B, mu Tx minus 3 chi x mu rho x psi x nu. Calculate these two for the equation, we obtain dl dr equals 4 pi r square epsilon r nu times rho r, and c times dB mu Tx over dr equals minus 3 chi r nu rho r times L r nu over 4 pi r square. Now if we define the total energy flux L r equals the L r nu integrate over all frequency, and correspondingly the energy per gram emitted by nuclear, the total energy per gram emitted by nuclear process epsilon r equals nu epsilon r nu. Introduce these two definition, we can obtain dLr dr equals 4 pi r square epsilon r rho r, and the second one is minus 3 rho r L r 4 pi r square equals C integral over d nu chi r nu partial B nu T partial T dt dr. Okay. Now define the Rosland mean opacity chi r. Opacity, whose definition is just the inverse of the average of the inverse of chi r nu with the weighting function partial b partial t. Chi r nu weighting function partial b partial t. Yep, this one. And notice one property of the Planck blackbody distribution for B mu T. We have learned in statistical mechanics that this integral is just 8 pi 5 power k 4 power over 15 c3 power times the third power of h times the fourth power of t, or simply at fourth power. This a is just this coefficient. And notice that in physics we can just generally exchange the integral and the derivative. We can only do this in physics. If you do such operation in mathematics class, the lecturer will not be satisfied. But we are do physics, so generally assume it's valid, and so we can exchange the integral and the derivative, and we can easily use this property of Planck blackbody distribution. We obtain minus 3 rho r Lr over 4 pi r square equals 4ac the third power of t prime over pi r. And we can obtain dt dr equals minus 3 rho r chi r over 4ac times the third power of t times Lr over 4 pi r square. So, wait a minute. Yeah. These two equations are just the fundamental equations of radiative energy transport in a spherically star interiors. And recall the hydrostatic equilibrium equation we have obtained in the last seminars. We can construct the radiant model of a spherical symmetric star. Radiative models. 4 equations. The first two is the hydrostatic equilibrium equation, dpr dr equals minus g mr rho r over r square dm dr equals 4 pi r square rho r. And the latter is the fundamental equations of radiative energy transport, dLr over dr equals 4 pi r square. Yeah, 4 pi r square epsilon r rho r dtr dr equals minus 3 chi r rho r over 4ca times third power of t times Lr over 4 pi r square. And we have 4 boundary conditions. M0 equals L0 equals 0 and rho r equals tr equals 0. This r is the star's nominal radius. Notice that, okay, I change of color. The function pressure, opacity chi, and this epsilon about nuclear energy, we can all these functions can be expressed as the function of rho and t. So we actually have 4 equations governing 4 functions. Rho r, mr, tr, lr. These 4 functions are governed by the above 4 equations, and the boundary conditions. And another thing that we should notice here, the so-called nominal radius. The nominal radius r is, you can think this is just where the rho and t would vanish. If the four equations held out to this radius, it's not necessarily be the same as the real radius of the star. Okay, so we have four equations with four boundary conditions governing these four functions, and we can obtain a one-parameter family solution. I.e. the Bode-Russell theorem. This theorem says that if the chemical composition of a star is fixed, then there exists a unique solution to the equations of the stellar structure depending on single stellar parameter. This parameter can be the radius r or the total mass m0. In practice, the m0 is more natural than r, so you can just make a little transform of these four equations and obtain this new form about m. dm equals 4 pi r square m rho m dpm over dm equals minus gm over 4 pi fourth power of r dl dm equals epsilon m dt dm plus minus 3 chi m lm over 4c a the third power of t times 4 pi r square. Yeah, just like this. And the new boundary condition Rm equals Lm equals 0 when at m equals to 0 and rho m0 equals t m0 equals 0. This m0 is the total mass. Okay. So for stars in generally speaking, for stars in an open clusters, they usually have similar initial chemical composition and age, and only differing in masses. So any two observables of these stars plotted against each other will be a one-dimensional curve, and each point of this curve will correspond to a stellar mass. And particularly when we draw the graph of the luminosity L against the effective temperature T, this graph is called the Hertzsprung-Russell diagram, or just HR diagram. Now notice that the effective temperature of T is actually defined by the Stefan-Boltzmann law. L equals O sigma T times 4 pi r squared, where sigma is C. This sigma is a Stefan-Boltzmann constant. This is the theoretical definition of the effective temperature, while in practice, estimation, this effective temperature is usually estimated by the star's color or spectrum. To understand this, we recall something we have learned in statistical mechanics that for large, okay, consider the Planck blackbody distribution. For high temperature T, in stellar physics, we always consider T larger than 30,000 Kelvin. T, then H nu over KT can be regarded as tends to 0. At this limit, the Planck distribution will tend to 8 pi KT nu square over the third power of C, and proportional to the square of the frequency when the temperature is fixed. And this equation is just Rayleigh-Jean's law. So when the temperature is high, we notice that when the temperature is high, the high frequency visible light has much more has much larger probability density than the low frequency visible light. So among the visible spectrum of light, the color will tend to blue because this color has the highest frequency in our visible spectrum of light, and that actually is correlates with another interesting problem that why the sky is blue. So let's put like this, yeah. Yeah, just like this. Why we have a blue sky just like this? So actually, the distribution function Fr for the light scattered by the molecules in atmosphere happens to proportional to the frequency, the square of frequency too. So in the same distribution function, the higher the frequency, the higher the frequency b, the larger the distribution function, or the same, or just probability density. So we will see. So we can see a blue sky just like this, and in this condition, we actually have another conclusion that sky blue is actually the asymptotic visible color of a black body at a high temperature T. Because in high temperature, the Planck distribution tends to the Rayleigh-Jean's law, and which is proportional to the square of frequency. In visible light spectrum, we will see a blue color, the same as the sky blue, just like this. Okay. So we have discussed this color and the color and the temperature, effective temperature of stars, and based on which we can classify the star, and we can obtain some type. We can set some type of star. Yeah. First, according to the effective temperature and the color. First, type O, with a temperature higher than 30,000 Kelvin and a sky blue color. An example is just the so-called lambda Orionis star or just a Mesa star. You can see the picture of it. This picture is taken from NASA. Okay. Change color. See, this star is just this Mesa. Its color is sky blue. And second type B, with temperature between 10,000 Kelvin and 30,000 Kelvin. And with a blue-white color. An example is Rigel star. We have its image as well. Okay. I think I should. Yeah, put on this. Yeah. See this one? It's the Rigel star. It's a blue giant, and the color is blue-white with the temperature between 10,000 and 30,000 Kelvin. A third type, okay, the third type, type A, with temperature between 7,500 Kelvin to 10,000 Kelvin, with a white color. The famous example is just the Sirius A Vega, one of the lightest stars in the sky, in the night sky. Let's imagine here. This one. Sirius A Vega, the big one. No, I should use red color, the big one. Okay. And type F. With temperature between 6,000 to 7,500 Kelvin. With a yellow-white color. The example is the Procyon star. I think it's this one. Yeah, this one. And then type G, with a temperature between 5,000 Kelvin to 6,000 Kelvin. And with a yellow color. The example is our familiar sun. Then type K with the temperature between 3500 Kelvin and 5000 Kelvin, and with orange color. Example is the Arcturus star. It's imagined here. It's imagined here. This one. Yeah, just this one. And finally, type M. With a temperature lower than 3500 Kelvin, with a red color. The example is the Arendelle star. Imagine. Where are you? Yeah, this one. Where is it? Yeah, just this star. Okay. So we have the star type from O to M, and I give you the image of each of the type of star and the color of it. Finally, let's display a complete HR diagram. Yeah, this one. Okay. So this is the so-called HR diagram, a diagram plotted by the luminosity against the effective temperature. Notice that the high temperature is in the left. Okay. Okay, in this HR diagram, we can find uh, this set of this set of main sequence, and our sun are in this sequence. Okay. So actually, I think today is enough. We have obtained the mechanism, at least the mechanism of the HR diagram, and show some beautiful images and the diagram itself. About the uh, how to estimate the diagram by the dimensional analysis. We may talk about this topic in later seminars, but not today. Okay, so much for this. This is today's astrophysics seminars.